Hey, welcome everybody. Like Sam said, I'm Mike Fremaux and I am retired. Distinguished, not in my title. So that minus two for Sam on that one. But today I'm going to talk to you all about, give you a little bit of an overview of the Flight Dynamics Research Facility. And I'm sure most of you are at least familiar with it at a high level, maybe in more detail than that. But if nothing else, you've driven by the thing and you come down the boulevard, a little hard to miss. Anyway, so I'm going to give you that overview. And what I'd like to do, I was telling Sam, rather than wait till questions at the end, which that's fine too, why don't we do questions as we go along? Keep it really informal. If you have any, just call out or raise your hand. Folks online, just speak up and we'll go from there and see how that works. So if everybody's good with that, let's get started. Just my cover page here, and I'm going to talk a little bit more in detail about what you're seeing in those pictures, but this kind of gives you a sense of how the thing changed from when we started just coming out of the ground in 2022, 3, whatever that was, to what it looked like actually more than almost 2 years ago, here on the bottom right. So with that, it doesn't move. Survey says, again. It worked in rehearsals, folks.
Plugged in here.
Yeah.
So this guy.
Okay. That's why we had a center chief technologist. Our technology question. So what I want to do today is, why are we building it? What's it good for? You can't really talk about FDRF without giving some historical context, a little bit of background, what came before it and what we want to do going forward. Talk about some of the design choices for the facility itself. I mean, it has some, I use the word unique because it's not, there have been other facilities that look kind of like it, but for its use, it is unique. Talk about the test techniques that we have today and what we want to have going forward. Give you some interior and exterior views of the facility that you may or may not have had if you haven't been inside. And then talk about the current timeline, and we're asymptotically approaching completion. If that seems meaningful to you. All right, so what do we ask for? Well, so you probably know that we have a vertical spin tunnel, a 12-foot low speed tunnel over in the east area on Langley Air Force Base. This is on one of the sunny days we had after a hurricane. Just to show you one of the reasons we needed to get out of that area over on Langley, right next to the back river. Doesn't flood like that all the time, but I've seen it many times. Several folks in this room have seen it many times. Knee deep to waist deep water over there. But beyond just the flooding, these facilities I'm going to talk about are quite old. They go back, their lineage goes back to the 1930s actually. It's the predecessor facilities even before that. But kind of the motherhood statement up there. But we wanted to maintain support for a broad array of NASA missions with these experimental capabilities for both captive and free flight dynamic techniques, which we specialize in this facility. But there are a lot of other uses over the years that we've found in the current facilities that will move forward that it can be adapted to. So adaptability and simplicity in some sense is what the watchwords that we used when we were working on the design of FDRF. So what were the required attributes kind of in the bullet form there? Designing flexibility and adaptability, as I just said, we wanted good flow quality. Well, what is good? I mean, in a quiet flow facility where you're doing acoustics or transition measurements and things like that, is one set of goodness in a wind tunnel. And then in the flight dynamics world, we're looking for something else. We're not looking for necessarily as quiet as you would have in a really high fidelity wind tunnel, but the current facilities have, frankly, pretty poor flow quality. In spite of that, they've been operating for 80+ years very successfully because we know how to compensate to some level for that flow quality and then, how to interpret the data. But we certainly wanted to have better flow quality in this new facility. A suite of advanced dynamic test techniques. Some of those things have been developing over the last several years, independent of the new facility, that they will now move to that new facility. We tend to work, frankly, in flow regimes that are still difficult for CFD. CFD gets better all the time, as everybody knows, due to the computational horsepower the techniques, the modeling, and all getting better all the time. But we still have a lot of corners of those envelopes where doing it computationally is very difficult, very expensive, and time consuming, and we can do it in these facilities. We always have had and always want to continue to have really rapid integration of our test articles, whether we're building them using rapid prototyping these days, moving them in and out very quickly. That's one of the hallmarks of the current and future facility. We tend to operate with a very small staff. We wanted to continue to do that with 3 to 4 people typically. That keeps our operational costs down, and et cetera. And then I already mentioned the models, but that's where the rapid prototyping is done. This is just kind of a smorgasbord without going through all the different things. You can see things up there that are either current or going to go forward, or maybe are not now, but they still give you a flavor for the kinds of things that have gone into the current facilities and will go into the new facility. You know, X59, kind of the poster child for the work we've done on the prototype X-plane series, whether, you know, all the X-planes going way back to these facilities. A lot of work on distributed electric propulsion, vertical takeoff and landing. X66 spent a huge amount of time in the 12-foot tunnel. In fact, they ran it so hard before we closed it, I think it literally put the last nail in the coffin in that place. You can't even turn it on anymore. But a lot of work on the space side of the house too. Examples like Stardust and OSIRIS-REx. A lot of work recently on Dragonfly, commercial space, Da Vinci, which is a concept for a Venus probe. As well as Orion, Apollo, Mercury, Gemini, et cetera. So what did we get? We asked for one thing. What did we get? Well, I'm hoping we're getting pretty close to what we asked for. We are going to get, it is state of the art in the sense of the type of work it's going to do. Vertical wind tunnel that has the capability that it has, both in terms of tunnel performance and the test capabilities. It is the first major tunnel built by the agency, not just Langley, since NTF, which opened in 1983. Yeah. And then, of course, it leverages the capabilities and the expertise from the current facilities, as I told you. Just to mention that, you know, the contractor team that we're working with, BL Harvard International in Birmingham, Mason the Hangar out of Richmond, and Northwind Systems, formerly Calspan, formerly ASE, formerly Fluidyne. Hopefully Northwind until the end of this project. Just name changes, basically. Has been a very good contract partner for us, and they're working very hard to finish this thing. Okay, so I've talked a lot about the legacy facilities. There they are up on the upper left. This is the 20-foot vertical spin tunnel, which has, you see the, back then we had blue tarp all over the side. That was to replace all the rusted I-beams that were all rusted out from the flooding. The 12-foot low-speed tunnels in the sphere, and then there are 2 auxiliary buildings here, 646 and then 645A, the office and lab building kind of hidden behind the spin tunnel. So we've got a 4-building complex over there, right on the banks of the Back River, elevation about 4 or 5 feet. What else can I say about that? The 12-foot low-speed tunnel is kind of unique. If you haven't been over there, it's in a sphere. People have asked, is this a hypersonic tunnel? Not if Mach 0.05 is close to hypersonic. But it was built as a free flight tunnel. So there's a test section inside a sphere on pivots with have hydraulic rams on it. They're used to, so you could pivot the thing around, and no matter how the glide slope of your free flying model was, you could match that. The pilots are in a booth on the side. You continually run the thing, and so that's why it was spherical. So as you tilted the test section, return path stayed more or less the same. So it's been well in horizontal position for many decades. So here are the performance characteristics here on the left: very low speed, 7 PSF, 8.6 PSF, maximum Reynolds number, etc. And what we're getting here, it's still not what you call high speed. But we're going from a maximum dynamic pressure of about 9 PSF to 35 plus. So we'll have a lot more capability there for doing free flight tests, as well as getting better signal to noise ratio on our force and moment balances. Importantly, we're out of the flood zone. Here we are at 12.45 feet, which is what we had to build it to, which is amazing compared to where we are at the old facilities. One of the ways, and I'll talk a little bit about how we got here contractually, but replacing those 4 existing buildings with buildings was a big part of the selling point, because we're combining capabilities of both of those tunnels into this one.
What do you mean by 30 by 60 site?
Okay, so this right here, it's you know, if you look that way, there's a huge open lot now. That's where the full scale tunnel was.
So that 30 by 60 tunnel.
Yeah, we interchangeably call it 30 by 60 or full scale.
Oh, that's the lot next to it, below that.
Yeah.
Oh, I'm sorry, I thought.
Built this way. Was the full scale tunnel. And if you drive by there now, it's all fenced in. The Air Force, of course, they always own the property anyway. There must be 500 tonics that's sitting out there, ID laid down there. They're doing a construction right now. We've got a time, a night or two at full scale. Yes,
Is
sir.
that a building that's in there, has that been turned over back to Air Force or?
Well, so we're in the process of moving out of the building. And last week, going through my boxes, and I've got about 100, 200 left to go, and everybody's in the same boat, but we're supposed to be out of there by the end of March. The brand's going to go with that. Once that happens, I don't know if they let the contract, anybody from COD here? The demo contract, but once NASA pays for it to get demoed, and then the property goes back.
That's not mine.
So I'll point one thing out, I don't want to get too long in the presentation, but you see the bottle field here? That stays. That's for EDT. That's the high pressure. They use the surface also the 12 foot and full scale tunnel, when there's pressure here. But there's no plan to move those, so I think what you're gonna have is a giant open lot with the bottom of the sea.
Man-made region.
So, this is a couple of pages of, you know, how did we get here? I'm not gonna go through all those. I just kind of want to make the point, if you want to see the chart, I can send them to you. Basically, people have asked me, you know, how did you get this thing built? Careful, I didn't get this thing built. A lot of people were involved with this thing built. I've been involved since pretty much day one, and as people have come and gone, I've kind of been the one concept of the whole thing. But there have been 3 times since the mid-90s. We had an opportunity in the mid-90s to put forward a proposal to replace the vertical cement tunnel. There was another one in the mid-2000s, and then there was another one in the mid-2010s. So it's like once a decade, these opportunities would come up. And what I finally figured out after the second time that we were told, let's do it, but can't do it, no funding, whatever, is that you always have your proposal ready to go, keep them in shape, keep the numbers up to date, do some work in the interim to kind of polish it up, and have it where when an opportunity comes, you change the date and you submit it. That's how this thing kind of came about. Between the mid-90s, when we did the first one, working with the old FDNO systems engineering, systems engineering and operations director. Mr. Swain, you remember Mr. Swain, Bob Swain? I heard he passed away. It was announced that he just passed away recently, but he was a director back then. He and my branch at the time, Dan and Dunham, spun up a team to look at replacing the facility, what would it take. So we did some research, we did some cost estimates, and we put forward a proposal. Jerry Green, I think at that time they'd gone up to headquarters, Code R. And so he took it forward up there and, gave us a lot of feedback and said, looks good. Just don't have the funding, but, try again when the next opportunity comes up. So fast forward to the mid-2000s, and let's see, where is it? Probably right here. ATP, the predecessor to AETC, had a call for projects, so I submitted it then. And it actually got quite far in the process, is my understanding. Alan Kilgore was leading that effort in terms of landless ATP activities. And about that time, my understanding is the Glen icing plant, the icing research tunnel died, or was about to die. So that's where all that ATP money ended up going. I hope I have that right. So once again, we were kind of left at the altar. So in the meantime, I worked with some contractors like Biggin in 2009 and 2011 to put together some more background information, do some studies on what would it take to replace these things, do some updated cost estimates, do some technical estimates. And so we got a really lot of good information there. By that time, The I-flight type tunnels you probably have become familiar with, skydiving simulator wind tunnels. We started calling them COTS, commercial off-the-shelf wind tunnels, which sounds good, doesn't exist, but those had come on. And so we said, that might be an opportunity for us to get that kind of expertise involved in this. So we did some studies, we rented time in the facility out in Seattle, actually. And got a lot of measurements and what kind of flow quality do they have and speed capability, et cetera. So I had all that done at that time, and then lo and behold, back in 2015 or so, I was part of the one of the capability leadership teams for flight mechanics that the NESC was running at the time. And so we put forward a proposal then that actually got vetted. But I think put us over the finish line that time was it got vetted by all 10 senators of participating, and participating in that team. And they all gave their kind of stamp of approval. They would support Lane putting this thing forward. So it went forward to headquarters and got approved at the engineering management board. Lo and behold, Lisa Rose was up there at the time for Langley. And so that's kind of how we got that in the 2020 budget. It was in the president's budget. So here we are today. The September 9th, 2021, the contract was let $43.2 million to that team already mentioned. Broke ground August 17th of 22, and then it kind of started coming out of the ground in that fall of January 23. So might put an asterisk by that. I'm hoping we'll be there.
To how Mike goes full circle, you talked about the I-flight skydiving tunnels and getting data from them.
Yeah.
Before they were ever built, they requested NASA to allow them to test out the concept in our vertical spin tunnel because it was a preliminary concept. And it, life went full circle.
Well, there you go. I didn't know that. That's cool. Let's see. All right, let's talk about the tunnel itself. So as I'm sure you've noticed, it's a vertical tunnel and it's a dual return tunnel. This is a schematic of the tunnel itself. So dual return clearly means there are two return paths, one on either side. This is not unprecedented. We've been talking about full scale tunnel or the 30 by 60. That was a dual return tunnel as well. They have been built. But the question is, why would you build one sort of a traditional single leg return tunnel like 40 by 22, for example? And from a flow quality and a power utilization and efficiency standpoint, that's probably still the best way to go. But when they started doing it, they looked at both. The contractor, I say, the designers looked at both single return, double return. And when the single return tunnel was looked at, you notice how tall this building is right now? It was about 40% taller if you went the other way. Let's just say the Air Force was having kids. They were not. And I'm not a structural engineer, but I can even imagine, the need, the flexibility of a tall, skinny building like that, and the how you have to build it. So the dual return here is what they settled on for that and other reasons, but it does make sense in this application. One of the differences between this and the I-flight tunnels is the I-flight tunnels have the motors and the fans up here in leg 2. Aerodynamically, what you probably want is leg 3, which is that's the more traditional spot. Put it behind this turn 1, turn 2, between 2 and 3. But again, mechanical motor reasons, bearing reasons, accessibility reasons, maintenance reasons, the ground floor made the most sense. So that's where they are. There are 2 on each side. They're 14-foot fans. I'll show you a picture of them. Each fan has a 750 horsepower motor to get us the performance. So then, once you get back into this settling chamber, you get the turning vanes, of course, like any wind tunnel. We've got a honeycomb, we've got screens and a contraction, and then the test section out here. So it's kind of traditional in that sense. Oh, I will mention one thing. We do have heat exchangers, active cooling in this facility, which is completely different than what we have in the current facility. So the idea there is we can cap the heat rise in the tunnel, whether it's because of a hot day or because we're putting energy into the flow with the fans at 79 degrees. So it'll drift till we get to 79, and it'll stop and it'll hold it there. So that'll help us with our data quality as well as just the comfort of the test staff. This is a ground floor schematic, just to orient you when you're looking at it. Langley Boulevard, here's the front entrance over here, so Langley's over here, Langley Boulevard. Lobby area, which is really the public space if you walk in. Everything else is back of the house, so on the front side, telecom, service quarters, storage, etc. You can walk through here. This is the tunnel in the middle. You see the four fans, you see the turning vanes, you see the heat exchangers here. And on the back side, we have our pump rooms for all the cooling systems. And we have our VFDs, or variable frequency drives. That's what drives the fans themselves, and that's how they're controlled. And then in the back of the yard over here, we have a 500-ton chiller. That's how we do the cooling in the facility. It doesn't really show up too well, but there's actually a sound wall here. If you remember where we're located, just to our left is building 1208, and that's where the acoustics folks are. So the second set of kits born when the acoustics folks learned that we were building right next door to them. But I have to say, those guys were really great to work with. And this goes back to 2016 timeframe. They were concerned naturally about sound and vibration coming from here. And that's up their human lab where they do the measurements, et cetera. And so we went down to the Virginia Beach I-Fly tunnel and crawled all through there, took measurements. Those guys let us go in to the guts of the thing, take measurements, ran it up and down. So they got a lot of just kind of quick data to do kind of a sanity check to see, okay, you're gonna have a problem. And based on that, they did some along the fence line that's over here towards 1208 off to the left. They came up with, okay, Flight Edge Research Facility, you shall not make more than X number of decibels at the fence line. So we had something to put in the contract. So the contractor has to meet that. At that fence line, they can't exceed a certain sound level at high speed conditions. So that's all been done. And that's part of the reason the chiller's on this side and it's behind us now. We also got a generator. It's nothing compared to like what's over at the computational research facility, but and it only fires up in a power. It's not for anything else. So once a month it will run for a few minutes. All right, this is the control room level. This is kind of we call it on the elevator. It says the third floor because the second floor is actually outside and getting to a catwalk. But it's the equivalent of 6 stories up. So this is really the where most of the people will be most of the time. This is the test section here in the middle. It's 20 feet in diameter. If you consider a 12-sided thing a circle, it's 20 feet across. And which is exactly what the current spin tunnel is. The requirement was it had to be between 20 and 22 feet. Well, naturally, a smaller one because that's what we're doing. So, but the big difference is we have so much area to work in compared to the current facility. I think I have it in here. This circle here represents the wall inside the control room, the current spin tunnel, versus what we have today. So I always think that's kind of cool to show the difference. But anyway, the room, if you will, it's one big open room, and that's the way we wanted it. We wanted it to be adaptable to other uses. The right side is kind of the industrial side, the model build-up, instrumentation, all that kind of stuff going on the right. On the left side, where you have your control consoles for the tunnel up here. You also have researcher tables. You've got displays, touchscreen displays. We have some desks in there now. No one's going to be actively living there in terms of their office there, but they will have desks for when they're in the building, like the technicians, for example. We also have a break room right here that is a glass wall, so you can kind of shut the noise out with a refrigerator and all that kind of stuff. The red text, that's representing all the things that are coming over from the current facilities. One of the selling points of this facility was we could reuse a lot of the test equipment and test rigs without having to reinvent all that. We have two somewhat one-of-a-kind test rigs, the rotary balance system and what we call the C-strut, which is it's an arc sector like you have with kind of a standard wind tunnel, but it has some dynamic capabilities on it that are not standard. So all of that has come over and been adapted into the tunnel. The very last piece of what we're doing right now is qualifying the rotary balance system, making sure it's performing the way it was baselined in the old tunnel. Excuse me. And The data systems and all this other stuff is already over there, so it's pretty much ready to go. So this is just, I took a picture in the back. In the lobby, the branch head, Corey Diegler had, we were supposed to go, they were supposed to go to the conference site last year with this. They built a 3D model, 3D printed model of the facility. It's like a giant dollhouse, you know, the big dollhouses that you see. And it's really kind of nice. And it really gives you an idea rather than a sketch of where everything is. This is kind of looking from the backside. So this is, you know, what's talking about the pumps and all that are in here. Here are the 4 fan motors in blue, the contraction section, which is outside, you can see it. The test section on the control room level, the rotary balance, you can't see the C strut, it's hidden, and then the return passage up here through the test section. If you here we go, it's behind, it's on the left hand case, which look kind of neat. Okay, test techniques. So kind of the traditional test techniques that we're bringing over. The spin tunnel was built to do dynamically sealed free flight. There were no test rigs in the facility back then. And here's a picture from back in the 90s testing the F-18EF Super Hornet for spin modes. You can see you have a spin parachute on it, spin recovery parachute. So that kind of work continues to go on in the current and new facilities. So now you have a small model and you're properly scaling the mass properties, the moments of inertia, the center of gravity, the mass, and all that, and free flying the model in the tunnel, and looking to see this have a spin. This is one for airplane, obviously. What are the spin recovery characteristics? We still do that kind of work. It was the last one that came through. Oh, it was I think it was Lockheed. That's who it was, and that was a year or two ago. So that's the free flight technique, but that's also used with the entry vehicles. This is a little hard to see black on black here, but that's an Orion capsule with drogue parachutes on it. So we look at dynamic stability of free falling, terminal velocity kind of activities for both human entry vehicles as well as science payloads. So more of that kind of work has been done recently in terms of dynamic modeling than actually aircraft. I mentioned the rotary balance already. That's called steady coning. So you can now mount a model on that rotary balance and you can rotate it at various attitudes and rates to simulate spinning motion, aircraft spin. You can measure the force of the moments just like you would in a regular wind tunnel. And you can take that data, you can predict the spin modes analytically. You can put that data on a simulation along with a lot of static data and other dynamic data that we're in daily simulation of an aircraft. And then finally, we do what's called combined motion, where there are certain cases, and this has come up several times, sort of in the entry vehicle world for Orion, especially under drogues, where you're coning, rotating about a vertical axis, a wind axis, but you're also oscillating at the same time. Very complex motion. And when they try to model that without actually doing the measurements that way, the models are not predicting correctly the motion of the test arm. For example, they drop near full scale test arms out of Yuma proving ground. So with this combined motion, we're oscillating and rotating simultaneously. We know we'll measure that data and more correctly predict the motion of the test arms. That's been in the spin tunnel. In the 12-foot low-speed tunnel, up here, upper left, static force and moment, kind of standard stuff there, although we do a lot of high-angle attack in that facility. We have laser light sheet and smoke flow visualization, because we have people in the room that know how to do laser stuff. And help us with that. We get nice images of vortices and things like that coming off a model. Force oscillation is 3 different pictures here: roll, pitch, yaw, depending on how you orient the model on the rig. This is on our C strut, so you can do body axis oscillations about all 3 axes one at a time and get that data. And then finally, we have a 3-degree of freedom rig, which is kind of a somewhat new technique. And this was actually a recent test of a powered model. I think they're the 6, a bunch of propellers on that thing. For doing vertical takeoff and landing. And so we can get the 3 degrees of freedom and see how they interact with the motors and the control system and all that kind of thing. And then finally, design of experiments. Of course, not a new technique by any means, but some of the things that they're doing in the facility. Is Ben Simmons in the audience today or online? He's kind of leading that charge in the branch, doing some really great work. It's some advanced techniques that are showing that they can remove the time for some of the dynamic data we need by order of magnitude. I mean, it's amazing stuff. Let's see, and this is just to show you the difference in the test rigs, the rotary balance on the left, the C-strut on the right. On the top row, that's how they've been installed in the current facilities. The rotary balance, it's shown in its park position. It's kind of nested up against the wall in these alcoves. You never can fully get it out of the tunnel because it was a retrofit. And the tunnel was built without any test rigs. And it's actually the third rotary balance that's been in that facility, but they've always been just nested up against the wall. So that really doesn't do well with your flow quality. When you're free flying the model to do the dynamic techniques I was telling you about earlier, these walls are in the old tunnel actually had padding on it, 2-inch thick, kind of like wrestling mat. Pretty soft. So with the spinning model, we're covered and hit the wall. If you try to minimize the damage to it, for some reason, about 85 to 90% of the time, it hits that thing. I don't know why. Even thing percentage-wise, it would be that high. It probably is. And here it is in the FDRF. I mean, I'll have to kind of explain what you're seeing. So the test section, the hook is over here. It's out of the test section, and it's fully retracted. And here you can see, here's what we call the beam, the rotating beam is right here, same as this. And it's on these rails up here. So it's suspended from the ceiling, fully retractable out of the tunnel. That's one of the ways we keep the productivity up in the new facility. Now we're replacing 2 facilities, so we can fully retract both of the rigs. We can be doing free flight testing while both rigs are out. We can inject one rig and test on it and be building up on another. We can swap them out. So that really is a way to keep your productivity up and have better flow quality at the same time. And then finally, the C-strut, you see it here in the 12-foot on the post is vertical here, coming up through the floor. Now we've had to turn it 90 degrees so the vertical is vertical. And so they've built a new insertion mechanism, and that also fully retracts out of the tunnel as well. So this is right along the center line of the tunnel. Any questions before we talk about the construction?
Back up, what is that corrugated tube on your?
I was gonna kind of get rid of that in Photoshop, but. So, all right, so this is 12-foot with all the cables, just hanging down on the floor, just like a rat's nest, but who cares? That's the way we operated for decades. Can't do that anymore. So that's to carry all the cables and the wires and all that. We really struggle with this. What do you do with that? And frankly, I don't think we have an optimal solution yet, but this is what they came up with. So it's a tube designed for data cables. It's separated inside, so you have your low power, low voltage stuff separated physically. But it just kind of dangles there, and it has a stand there that kind of holds it off. We have a little bit of flapping at certain speeds. Move around. We're gonna have to fix that, but that's how we're managing the data cables, power cables. Okay, so back to the kind of the first chart I showed you. This was January of 2023, just starting to come out of the ground with the foundation. One of the things I didn't mention, how's the time going, Stan?
Good.
Okay. Is the building is made out of precast concrete. That's not what we were thinking at all when this first came up. The I-Fly tunnels, for example, we've seen those under construction and visited some sites, and those are kind of traditional steel frame buildings that have a cladding on them, and you build them just like a kind of a regular building, except it's on the side. Well, when we got our proposals and I-Fly was not picked, or the company that does the I-Fly tunnels was not one of the contractors. This one proposed the precast concrete. Everyone's saying, wait a minute, that's what you build parking garages. We want a lot of precast concrete. So we COD folks that know something about building constructors did a lot of background research and said, this could actually work. And so as it turned out, it saved a lot of money and it saved a lot of construction time. Because if you were coming in every day, kind of week to week, you probably notice how fast the building changed. the trucks would come through the panels there. I forget the measurements on our former project manager, Dave Stork, was here. He remembers the size of those panels. Most of them were about the same size, but they were built up in near Petersburg, Virginia, at a plant called Tyndall. And they were trucked down 2 or 3 or 4 a day, one at a time, one per truck. I had to turn them up at a 45, get the gate, they took the gate down one time. So. But anyway, so as they came, we had a big crawler crane, the big yellow thing here, which set them on in their spot, kind of like a tinker toy. And the welders would go to work attacking all the tabs and weld it up and go to the next one. So it went up rather quickly. So you can see from early January of 23, this is March 24th. We're pretty much poking out of the ground. This is the outline of the tunnel, the back room, the front room's all there. By June, you could really start to see what it's going to look like. End of August, everything but the top piece and the control room are on. And by the way, they have now set the contraction. That contraction cone is the only significant piece of steel in the whole facility. It was built off-site, obviously, in a factory, I think up in somewhere up north. I forget exactly where, and shipped down here in pieces in connexes, and it was built on this slab here. They built just for setting things up, and that was picked and set down in between these columns with 6 inches or less to spare on each side. It had to be on a very calm day, very slowly. Got it down there and set it. And once that was done, the rest of the building went together. And so here we are in, was that 11? So if I recall, November of 23, the building is kind of complete. They exterior building. So 11 months, the building's up. I thought that was pretty good. The blue stuff all down here, that's when the fans were delivered. Those were built in Germany, Stuttgart, and they were shipped again over in big boxes and assembled on that pad and then installed using the crane as well. So it's kind of, see if this place, maybe it's here. This is the roof of the fan rooms right here. So the design is, if we ever have to get the roof, the motors never died and the fans don't throw a blade. But if they ever do, the roof of the thing is designed, you go in there and cut the tabs. You have to do that, and then the crane just comes in and picks that whole panel up, maybe it's 2 panels, and then we have direct access to the motor. So it's relatively easy, designed for being opened up that way rather than, cutting a hole where you didn't wait 10 hours. Trying to think ahead a little bit. So I like to show this because, for years, a couple of years, we had this drawing, here's what's going to look like. And then I took this picture when the lighting was somewhat similar from a different angle. I cropped the porta potties out. Okay. And a nice little night shot there. I was mentioning the second floor. There's an elevator stop right here. You see a catwalk. So because the free flight test, if something ever gets dropped into the tunnel, we got FOD procedures and FOD protection and all that, but inevitably something will break off of the model and fall down. It's going to be on the top of one of the flow screens. And so where we're going to have to get at that, we have a series of hatches. There are 2 on each face of the contraction, so the technicians could come down here, get on the catwalk, open those hatches. And what we're envisioning is a long pool skimmer where you can reach out and pull it back. I tested that theory with my glasses a couple of months ago, and we're going to need a big pool skimmer. That screen is 40 feet across, and it didn't sound like it was going to be too bad to get it, but of course it's landed right in the middle of that. It was not easy, so we got to come up with a good system for that.
But it did punch through the screen? Yes. Like sit on top. Oh, that's good news.
Yeah, I was worried about that.
Kina, turn up the speed and catch it up. Yeah.
Well, so in terms of FOD, a lot of more likely like parts coming off of a model while you're testing, they're going to go up. So we have 5 screens up on the turning vanes. And those are designed to catch anything that flies up so they don't circulate around back into the motor.
You don't have the old claw that we use.
We do. We still have it. We thought we were going to be able to get rid of it. I told them don't throw it quick yet. We still have the claw, the model retrieval claw. So here's some pictures of kind of, these were taken about 2 weeks ago, I think. Right. This is, I was up on the there's a mezzanine in there when I get up to the roof, but this is looking towards the control consoles, which are over here, and to the left are some of these researcher desks that we have, people can use. And this is, of course, looking from the control consoles into the test section itself. We've got your monitors up here that can show various camera views. This is just panning to the left a little bit. This is the rest of that area. We have a couple of tables with those screens I was telling you about. Just some seating over here. Folks want to sit there with their laptops. This is the subfloor, which, you know, you think, why did you show us the subfloor? But this was not originally part of the design. This was going to be open space. And then with some conversations with the contractor, we realized that, you know, we really don't want these Vicon cameras. I didn't mention the Vicon cameras. We use those, which I'm sure some of you used in your labs. We use top and bottom Vicon cameras to track the free-flying models, to get position and attitude data. We didn't want those sitting out in the weather, so they decided to close the subfloor, which was great because we moved a lot of the control boxes, the PLCs and all that stuff down into there and got them out of the control room. So it was really nice to do that. It's a kind of a low ceiling. It's about 6 foot 2 inch ceiling there. And these wire racks that have little dowel or threaded rods sticking down are real head scratchers. So very hard to have. So we have our laser system, our smoke system down here. I mentioned the laser already, but this is how you inject the smoke. There's a horizontal hatch, kind of tell right here, comes off. You inject the smoke on there, it can move laterally, it can move in and out to put the smoke where you need it. And then the laser light sheet, of course, is above that. Then there's the cabinet for the laser. That's all enclosed here. That can be moved up to the laser window when it's in use, and when it's not in use, it's pulled back, and there's a cover for that. And the reason we don't leave it there is because we have free-flying models. We also do prop testing for all of the power stuff. We've got a requirement that it has to be able to take certain impacts from lost blade and stuff like that. So the laser window is not up for that. So we have that covered. We're not doing laser stuff. We have a curb key system like probably all the tunnels do. So you can't get somebody can't get trapped down in the bottom when they're down there doing some maintenance. So if a curb key is out, which you will need to open up, for example, the fan room, you're not going to start the tunnel. So it's a safety system. And there's our little break room, which the contractor is using right now, kind of as their office space. The lobby itself, this is my favorite part. They actually let me touch some of this stuff. They don't let me touch any of the technical stuff anymore. But this is the lobby area. As you walk in, we have a historical timeline, starting on the right, back to the predecessor facilities, which goes back to the 20s. And it's kind of hard to tell. It's a curved wall, okay, as you come around. And the background is, you know, the black and white kind of sepia tone to color aerial views of Langley Air Force Base, Langley Research Center. When you're in the building, you'll be able to tell what it is. But we tried to tell the story of, you know, what was tested, who were the people involved, what were the timelines, what were the impacts in the pictures. So each picture has a little descriptive didactic panel that describes all that information. So that's really kind of neat. And it ends up, you know, as the old tunnel's closed, FDRF is now on this touch screen. We're going to have all kind of interactive videos on it, talking about what's going on today, what's planned for the future, that kind of thing. We also have a model display cave here. It's still being populated, but we have models that go back to the biplane era, up to, you know, all the space stuff and everything in between. A lot of neat artifacts, and it's going to be a rotating display because we have way more than we can display here in storage. So, you know, a lot of the tunnels, because they have bigger models, we're not able to keep a lot of stuff. Unfortunately, they had to either destroy them or do something with them. Because ours were small, we stored them way up in the attic for all those decades, and really glad we did. That's the model tunnel I was telling you about earlier. We saved the blades from the two facilities. The spin tunnel blades, which are these three here, it's not as cool a display as I had hoped, but the idea was that the break room is behind it. It was going to be sort of a divider between the break room and the main area. Does anybody want to guess why they look different, the middle one versus the other two?
One's facing the flow and one's facing downstream.
Yeah. So this is all the pot marks and Bondo repairs from all the model parts that got liberated and hit the fan going through. And here's the backside. So there's a difference. Old Joe Powers from the model shop used to reach out there on that catwalk, patch stuff up, and kept it going. And then the 12-foot blades, that the 6-bladed fan are here. And if you've ever been in that facility, the whole idea of this display was if you were in the control room looking through the window, this is what you would see. You'd see the back of the blades and you'd be looking into the test section. So we took a photo. Dave Storch, the former project manager, had this idea. He took a photo and we blew it up and made a giant graphic. The ceiling is 16 feet tall in that room. So it's a very large display. And so it's kind of made to look like you're looking through into the tunnel test section itself.
That is really cool in person.
Yeah, if you've seen it in person,
Dave, that was a great idea.
it really was. And then just, this is from the control room level, just thought of some of the views you have, kind of nice views of the center. If you go up to the top on the catwalk, it really is good. You can see all the way to the whole facilities on Langley Air Force Base. And then finally, the fans, the 4 fans, that's actually Dave for scale. They're 14 feet, they're carbon fiber, they're 8-bladed. You know, all those former blades in the old tunnels, and I assume most of the, maybe not ATF. What kind of blades is ATF?
Fiberglass.
Yeah. Usually it's Sitka spruce tradition, right? But these had to be very light because we do the free flight testing and you have to change the flow velocity very quickly to account for changing the aspect of the models and pitches up and down or rolls. We had to go change the RPM of the motor very quickly, so we had to keep the rotating mass as low as possible. So they're carbon fiber foam filled blades. We bought an extra set, matched that just in case. That's in storage. But they're light but very tough. And we already mentioned the motors themselves. They're ABB motors like you see in any industrial setting. All right, project timeline. I talked about the award in 21, who got it. It was a 2-phase project. I didn't mention that earlier, but we had phase 1 was build us a wind tunnel, prove that it works, prove the flow quality meets the requirements. Then you can go to phase 2 and integrate what we call the VFE, the government first equipment, the test rigs, the data systems, and all that. The idea behind that was if the tunnel was a fail, and we didn't want to, completely demolish or get rid of the old facilities until we're sure we had a new one that worked. Kind of worked that way, although we kind of let them go in a little bit earlier than planned to get the GFE going in phase 2. But essentially that's the way it did work. So we're kind of completing phase 2 right now. Right now, the current status, late February 26, project achieves substantial completion. That's a desire. It's possible. I'm thinking it might drift into March, but substantial completion. I didn't know any of this stuff until I got on the project, but that doesn't mean everything's done. It means to turn it over to the government. It means there's still paperwork to do. There might be a punch list left to do, but it's essentially the government can move in, the customer can move in and start doing what they need to do to start operating the facility, doing their qualifications and all that. So still contractors will still be around, but NASA will have access to it. In March, the branch trucks will be in there doing their flow surveys, which is already been done by our contractor, but we need our own to really understand what's going on. My understanding is April 10th is now a ribbon cutting date that holds. Be there, I hope. And then in the summer, I won't say beginning, middle, or end, but sometime in the summer, we're going to consider operation. So they've already got some customers lining up, or chomping at the bit, and hopefully by the summer. And so sometime they'll be actually able to submit it. That's it.
You got 10 minutes for questions?
Yes, sir.
Well, I'm gonna ask the obvious irreverent question, how likely are people to be able to free fly within it, and how likely could they be in the future in our seek for reimbursable funds model to participate?
So I'll give you a multi-part answer. technically, we have just enough airspeed to fly somebody. We can get to about 120 miles an hour, firewall thing. And that's, Steve's our resident skydiving expert. That's max drag condition, right?
Correct.
So there's that. The second part of the answer is, the facility is not designed with any of the safety features for people. So there's that. So there are no plans to put people in it.
How many people have been in?
None. No, seriously, nobody has done that. It's a good question. I mean, I can't tell, I probably did 500 tours of the old tunnel in my years here. And almost every time someone's like, can you fly in the tunnel? And my cheeky answer was, yes, you can, but it's a real short trip down to the net because we can only go 60 miles an hour in the tunnel. But I can tell you that the net was man-rated unintentionally one night on second shift too. But we don't want to do that again. So yeah, that's kind of the answer. No people.
That's what stopped when the predecessor company wanted to use the tunnel.
Yeah.
That's the legal statement.
I'm sure they can. Yeah, Karen.
Okay, I'll answer. I was curious, you mentioned the prefabricated concrete and going away from steel. Does that have implications long-term for maintaining a facility like this? And we have hurricanes and all this, I feel like I can imagine lots of cracking,
So I'll give you my semi-educated, but not qualified to really answer from a structural engineering point of view answer. My understanding, and I'm serious, is that maintainability and maintenance, this is actually an advantage. There's no paint. We
Yeah.
never have to paint the thing. That's a huge cost of this with language. Steve knows that. No paint. There is potential because each panel has a seam and there is caulk. And it's not the stuff you get at Ace Hardware, but nevertheless, we know it could degrade and could get things like that. We actually have a plan. RD has purchased some drones for interior inspections, so you may be familiar with that. And we're going to fly one of those interior drones in our return passages to look at the interior, especially those caulk seams over time. We're going to baseline it with the LiDAR and the video, and then look and see, are we getting any changes? Hurricane, we meet all whatever the hurricane, GSA has their building requirements, their P100, whatever that book is. We meet all those. So I don't personally think there's going to be any issue with the precast concrete, but I'm retired, so whatever I say don't matter.
I really do like this. I think it's going to work out great. Time will tell. And from a transformation standpoint, nice, flat, we can get off the shelf wall climbing robots that can, it's one of the few applications here at Langley that we actually can get robots right now to do a lot of management.
Cool.
Yeah, any plans to fly the autonomous flow survey probe?
Yes. I've talked to, well, Steve could give you a better answer, Steve Riddick in the back, but I know they've been talking to the folks who've been working that. Lou's been pushing that rope for a long time, and it's a great idea. But yeah, I think they do. Anything to add, Steve? Okay. Yes, sir.
So in the vertical sections, or I guess throughout the circulation of the tunnel, there's like no interior bladder. It is concrete. The flow is essentially.
Yes. Well, yeah. Everything's the contraction is steel. The test section is red. The diffuser, what we call high-speed diffuser, right above the test section is part metal, part concrete, and everything else is concrete. So, but we have a steps and gaps requirement, pretty stringent on the contractor. In any of those transitions, they get no forward-facing steps, and the gaps could only be so big, and the backward-facing steps could only be so much. So they had to follow that.
The original C-strut 12-foot was designed, built, and installed to be removable, and it was removed a few times so they could still pivot. And that did that design help you in reusing it, getting it across here?
We thought it was going to, in the end, when they pulled it out, it's on its
Yes.
stem. And he's right, it could be removed. I mean, a couple of technicians could take 4 hours or something and disassemble it and pull it out. But they were not able to reuse that piece of it. They had to, the arc sector's still there, but because they're putting it out, it's going from a 12-foot tunnel to a 20-foot tunnel, and now it's horizontal. They had to build a new post and beef up the post. In fact, the original post all the way out to the arc sector was about that big. We said, no, can't do that. So we made them taper it back a little bit, but yeah, I mean, it helped them in the sense that when they looked at what was over there and how that one could move up and down, because you could move it up and down with a split and a switch. That did help the design. Yeah. Hey, Gary.
Is there any need or plan to characterize the flow and the curves or anything? I'm just curious.
We don't have any plans the branch doesn't have any plans to do that, but I will say, when we started running the fans over here and they were starting, is it meeting our maximum performance? Is it, all that stuff. First thing all of us noticed was it was this high-pitched tone. It to me, it was like someone was taking an ice pick and shoving it in my ear. I mean, it was terrible. And we're like, there's nothing in the requirements that say you can't have a tone at X frequency, but they recognize that this is not going to work because we have a requirement. You don't have to wear hearing protection when the facility's operating unless you're running with the doors open, which we do on certain things. Anyway, to your point, so they started doing a lot of flow surveying and, looking at different things that causing noise, and they finally got an acoustic array up there on those behind turn one, between turn one and turn two. And it turned out it was the trailing edges of turn two where this was coming from. And they came up with a fix, and it wasn't bumps like you put on a wing to trip the flow, but it was basically a strip that interrupts the flow enough and it killed the tone. Kind of crude, but it worked. So it's attached and riveted up there. But that's the only kind of flow measurement that's been done. And I don't know that we have any plan. I say we, the branch has any plans to do that. And you asked because you have a way to do it.
No, I'm just, monitoring complex systems, short-term and long-term.
Yeah.
I'm wondering if there's, an oscillatory thing where the pressure wave moves left to right over, who knows, right?
Yeah.
I'm just curious if that was instrumented or needed at all.
Could be in the future. I mean, early in the design, there was a concern based on experience way back in 14x22 of a low frequency oscillation that rumbling, if you will, or something that, and could we have that here? And then a lot of CFD work was done for what it was worth to try to eliminate that possibility. But those kind of things do crop up.
But just out of respect for people's time.
Yeah.
Next speaker. We do have the room till 1 p.m. So if you want to stick around and ask no questions. Also, Mike is actually, so this is part of the AIAA Hampton Road section. We do have a tour next week at the FDRF. There's a couple of spots open. Please come over if you have any questions or you want to talk about the board next week. Yes.
Nice presentation, Mike.
Hi, Lou. Thank you. I was probably names are going to be bad. Who's the guy who took the flow probe kind of lead to that? Chris Meeks. I saw him at Tire One not long ago, and I didn't get a chance to talk to him, but I know somebody was talking about the whole flow survey probe not that long ago. And so I know it's still on people's minds.
Yeah, that's also along with your possible system ID testing in the car too.
Yeah.
Yeah, thanks for your patience.
No, thanks.
Yeah, hopefully you're enjoying retirement.
I am. I just want to get this thing finished.
It looks great.
Yeah, thanks. Yes, sir.
Yeah, thanks for the talk.
Yeah.
Is it possible I could get a copy of the charts that you shared?
Yeah. Let's see, can you give me your email and I can, well, I won't be able to email them if it's too big. You need the PowerPoint or you could have, was a PDF
Yeah,
okay?
I think a PDF should be fine.
Okay, how can I get them to you?
Yeah, I guess, is this your laptop here? I can.
Yeah.
Write that down.
You're welcome, Miss Chris. Hey, Ben. Thank you. Let's see. I'm gonna mouse back over here.